Okay, this one is a binomial versus a geometric distribution. So let's see, we'll just go ahead and get started. So the probability that Pujols hits a homer on any given at-bat is 0.12, and each at-bat is independent. What is the probability that the next homer will be on his fifth at-bat? Okay, this one is a geometric probability setting because versus the binomial. I'll explain the difference between the two. So each observation falls into one of just two categories, whether he hits a homer or he doesn't, success or fail. And the probabilities are all the same, and they're independent. And this is the important one for the geometrics, you guys. The variable of interest is the number of trials that are required to get the first success. So this is asking, let's go back here. This one is asking, what is the probability that the next homer will be on his fifth at bat? Okay, so so we're looking for the interest is the number of trials required for the first success. Okay, so when it is that, you guys, then we use the geometric probability, which is this is 1 minus p, so it would be the 88, the 0.88. And I think it said fifth at bat, so this would be 4 right here, and this would be 0.12, okay? So we're going to plug all that in right there. We're going to use that formula. So the geometric probability, where, yep, everything's all good. So we get a little over 7%, so 0.0720. Okay, what's the probability that he has exactly one homer in 5 at-bats? Okay, so it's not asking on which at-bat he gets that one homer in. It's just saying he has exactly one. So when it's asking a question like that, it's a binomial distribution. And when it's a binomial distribution, it's the same, except it's the probability of success on any one observation. Okay, so this one I just used a calculator on this, and Binomial Pdf, which is found under distribution, which is your second function vars. And in my calculator, it's 0, which is right underneath number 9. So n was 5, p was 0.12, the number of successes. We just wanted one success, one homer on that. So we plug that in for that one right there. And so if we do that correctly, you should get 35, a little over, almost 36% right there, 0.3598. Okay, what's the expected number of homers in every 10 at-bats? Okay, this is just a mean one, you guys. So it's going to be 10 times the probability, so 10 times 0.12, which is 1.2. So the mean number of homers for every 10 at-bats is 1.2. Okay, so what is the expected number of at-bats until the next homer? Okay, that's when you do the 1 over, I'm sorry, this is 1 over p, you guys. This is not 1 over n. This is 1 over p. Right there. Let me change that right there. So it's 1 over the 0.12, which is so 8.33. So the mean number of at-bats before hitting his next homer is 8.33.